Hello and welcome to Autology, the podcast that brings you the latest on automotive technology. I'm Anna Buettner, and this episode is called Electric Motor Technology and Evolution of the E-Axle. Here with me are today's guests, Graham Evans, Director of Electrification Technology Research within S&P Global Mobility, Jason Schneider, Principal Engineer and Team Lead, Electrified Powertrain at Drive System Design, and Paul Sims, Chief Technical Specialist, Electric Machines, also of Drive System Design. Hello, and thank you for joining this episode of Autology.
Hello, Anna. Thanks very much for having us.
Yeah, hi, Anna. Thanks for having us.
Hi, thanks for having us.
Yeah, good to have you all here. So this podcast will focus specifically on the role of motor technology in the transition to electrified vehicles, and in particular, how the design and development of the electric axle, or so-called E-axle, is evolving to meet the needs of future battery electric vehicles. This is a highly competitive and fast-moving technical area in the industry right now. So it's great to have a leading independent engineering consultancy and service provider with us today in Drive System Design to help us unpack this, coupled with S&P Global Mobility's research perspectives. And Jason, maybe if we start out with you, could you give us an overview for those who are not familiar with DSD's business, your area of specialism, and your global presence?
Yeah, of course. Thanks, Anna. So DSD, Drive System Design, we're relatively small, although we're growing pretty quickly these days, engineering consultancy, as you mentioned, and we specialize in driveline engineering and development. We've got two main locations, one in the UK, one in the US, and we serve a variety of customers in a variety of industries. So OEMs, tier ones, tier two, sometimes startups, and we touch a lot of industries, as I mentioned as well. So automotive, of course, but also commercial vehicle, defense, aerospace, off-highway, and a lot of what we've been doing, let's say, for the past, seven or so years has been electrification focused. The company as a whole is a little over 15 years old. We historically were a very transmission-focused company. We are known as gear specialists. So we have because of that, we have a very large mechanical engineering team, and we have sort of a very first principles approach to a lot of what we do. But we do have three other functions within DSD. So the one, mechanical engineering, like I mentioned. We also have control systems. So, that's controlling transmissions historically more. Recently, it's been sort of supervisory control systems for hybrids or EV systems. We have an electrified powertrain group as well. So we call that EP. So in the EP group, we focus on motor design, power electronics design, and motor control. And then finally, we have a development and test wing as well of our business. And the reason we have that is because our services are, blank sheet to A sample, B sample, hardware and development. So we offer sort of services all under one roof to get our customers, to help develop our customers' technology. Again, most recently, very much in the electrification space.
Great. Thanks for the overview there. And Graham, from the S&P Global Mobility side, would it be possible to provide some high-level figures around these industry sectors to give some context to how the market is evolving?
Absolutely, Anna. Yeah, we'll be glad to. So, we'll talk a bit about electric vehicle growth and also touch upon the medium heavy duty space as well that we track within S&P Global Mobility. So maybe a few numbers, high level on a global basis. So maybe starting with, this is production data, not sales, and we'll talk about light passenger vehicles first. So up to 6 tons gross vehicle weight. We expect that in 2023, around 11.6 million fully battery electric vehicles will be produced. really, to give that some context, kind of global market is about 88.5 million vehicles produced this year. So think about that maybe more broadly. Of that total, we expect about 28.7 million electrified vehicles. So that's a vehicle requiring some form of electric motor, be it a mild hybrid, a full hybrid, a plug-in hybrid, or a battery electric vehicle. So that's 32%. 32% of the global market in 2023, the vehicles produced, we expect will have some form of electric motor. If we take that out to 2030 and think about the growth of electrified technologies, we think that number of battery electric vehicles produced in 2030 will be around 47.2 million of a total, against a backdrop of a growing light vehicle market of 97 million vehicles. So by that point, about 72.6 million are electrified. So that's 75% of the market we expect will be either, say, full hybrid, mild hybrid, plug-in hybrid, or EV. So really 3/4 of the market at that point requires at least one electric motor, let's say. If we go into motors more specifically, about 42.2 million motors will be required on light passenger vehicles that are electrified in 2023. And of these, about 15.8 million are e-axles. So we mentioned about the electric axle earlier. Of course, in, let's say, all-wheel drive, four-wheel drive configurations, there's more than one e-axle per vehicle. So of those 11.6 million vehicles, we expect 15.8 million e-axles. Again, take that out to 2030, we're talking about 104 million motors for all these electrified vehicles, and about 60.7 million of those are e-axles. So, a huge growth area driven by this transition to electrified propulsion. Maybe to give that a bit of context, in terms of transmissions as well, obviously we know historically, DSD mentioned there the importance of the transmission market to them. And, we go back to 2010 and let's say, the electric vehicle requires a relatively simple reduction gear, often typically one speed, sometimes 2 or 3 speed, depending on the application. They were 0.2% of the global market in 2010. And then by 2030, we think that, in line with EV uptake, about 49% of the market will be taking a reduction gear. So really, this is at the expense of conventional manual and automatic transmissions, which in 2010 made up 89% of the market. By 2030, we think that they'll be about 25%. So we see an increase in some of these alternative transmission technologies like dedicated hybrid transmissions, some dual clutch transmissions within that automatic space. But as I say, only about 25% of the total market will require a conventional transmission of sorts by 2030. Maybe a brief stat on the alternate propulsion space in the medium heavy duty market. So again, thinking about 2023, we expect that about 3% of the market will be electrified, so either hybridized or fully electric. And by 2030, that's around 14%. So medium heavy duty space moving considerably slower than the light passenger vehicle space. Obviously more established diesel powertrain business, and taking longer really to produce an alternative powertrain that really meets the different use cases and requirements of the medium heavy duty space. So yeah, that would be an overview of the landscape as we see it and how we expect it to grow out to 2030.
Yeah, I might jump in real quickly to comment on something Graham said about the transmission market. So yeah, everybody knows that the transmissions are getting, let's say, simpler in the electrification space. And I've heard at conferences and many people will sort of say, as an aside, half joking, that transmission engineering is, not the thing to go into, right? Because we're not going to need these complicated transmissions so much anymore. I tend to disagree because they are smaller. They are less of the overall cost of your system. Because of that, it means that most people actually want a very made for purpose optimized transmission for their application. So the days of having, these 9-speed ZF transmissions that are used by many OEMs and millions of vehicles are maybe behind us. But I think what it means is that each application is really going to actually benefit from having an optimized solution in the transmission space to get the best out of that vehicle, the best out of that motor, and the best out of the application that it's supposed to be operating in. So I think we're going to get into a spot where, yes, these big complicated transmissions are out of style, I guess, but there's going to be a lot more sort of customized, optimized individual transmissions to suit a given vehicle application. So I would say it's a good time to go into transmissions because I think there'll be a lot more variety, and people are going to be willing to invest in getting that optimized solution for their application because it's just fundamentally going to, it's not going to cost them as much money.
All right. Very good. Thank you both for your input here. Okay, so moving on, maybe let's dive into some of the key tech trends around the electric motor. And it's great that we have Paul's expertise here. Paul, focusing specifically on road-based transportation, let's say, could you help us understand the main major electric motor types being put to use in electric vehicles and some of their pros and cons?
Of course. So the majority of applications tend to use permanent magnet machines, and that would be a lot of the applications that you may be able to go out and buy sort of mainstream manufacture. And they have very good torque and power density, but particularly efficiency. So the energy in versus energy out is generally better than other types. And that has a key effect, particularly on the vehicle, where range is potentially limiting the use case of the vehicle. So even a small drop in efficiency in the motor can lead to a significantly larger battery being needed in order to achieve a certain range, and that has pretty significant knock-ons to the rest of the vehicle engineering. So there are some notable exceptions that use or have used induction or asynchronous machines, and they are very robust, reliable, and maintainable motors. They see a lot of use in sort of mining equipment, and an awful lot of stationary sort of non-transportation applications use induction machines. Unfortunately, they do suffer a little bit in sort of real-world efficiency. So although kind of the peak efficiency, you may be able to tune and optimize it to get it in the same sort of ballpark as a permanent magnet machine, when you're actually running it in a drive cycle, in an operation in a vehicle, that the kind of the real world efficiency of that type of machine is, it just takes too much from the battery, or requires such a large battery compared to a permanent magnet alternative. So they may see limited use in, for example, secondary axles. So in a four-wheel driven vehicle, if you have two axles, you generally two driven axles, you may bias one of the axles to do a lot of the work, and then the secondary axle only comes in when needed. So a lot of the time that secondary axle isn't doing a lot of work. Now, if that were a permanent magnet machine, and it's still spinning, it's still connected to the wheels, it's producing energy and losses within the system. So typically they're used with some sort of disconnect between the wheels and the motor. So when they're not being used, you minimize the sort of parasitic losses. That disconnect comes with package constraints, cost constraints. So in such a vehicle, where using an induction machine in the secondary axle, that may very well be a better argument, as you don't need to do the disconnecting. Although there are still losses from spinning the rotor and the elements connecting it to the wheels, the deficit in energy and the loss or the need to not have a disconnect kind of outweighs some of the detriments to the slightly lower efficiency. A lot of these machines use hairpin winding these days, so bar wind conductors in the stator, which is generally a bit more suited to automotive manufacturing processes and timing. But it can be quite challenging, particularly if you're a large vehicle manufacturer looking at a family approach to motor design. So trying to reuse the same motor across several different platforms, in that if you scale the motor, make it longer, for example, for a higher power, higher performance application, you may lose out on flexibility on how you actually configure the winding in a hairpin. They are very, rigid in how much you can adjust them. So it is quite a challenging balance to play in sort of a larger application arena. A lot of the differences tend to be around thermal management. So at the kind of lower end of the market, the more heavily cost-conscious applications, you may see relatively simple cooling mechanisms. A water jacket around the outside is the only cooling mechanism, and that will save cost in the vehicle, but it may limit performance to a certain extent. Up to the other end of the scale, where you have sort of direct oil cooling and spray systems that are cooling the winding in the stator and elements of the rotor. And yeah, you can see that broad spectrum across a wide range of applications. So sort of motorsport applications, for example, tend to be focused very much on minimizing mass, maximizing performance. So they will use these high performance cooling mechanisms to as an overall benefit to the vehicle. And similarly with aerospace, where the three priorities are mass, mass, and mass. So it's just trying to get the best performance out for a minimum package. We get involved across a range of these kinds of applications, so it's quite good to be able to see a diverse range of applications and a diverse range of solutions that we get involved in. So these trends are quite common across different applications and different markets. So it's quite useful to be able to bring that experience and knowledge to the projects we work on.
All right, great. So really a variety of tech that largely suits a variety of applications with decisions made based on usage profile and performance parameters, but also naturally cost constraints, as you mentioned, Paul. Graham, how does this square with S&P Global Mobility's perspectives on demand for these different technologies?
Yeah, thanks, Anna. Yeah, hopefully we can put some market numbers around these, and I'll major on the light passenger vehicle space, I think, because that's certainly where we have most data and where a lot of our research is focused. So maybe on the e-motor tech trend generally, thinking about those, the permanent magnet synchronous versus the induction motor or asynchronous, as Paul laid it out, we're kind of in agreement. This induction market is only around 5% of the total motor market in 2023. We expect that will grow out to about 6% still by 2030, obviously against a backdrop of a growing market. And we do certainly see that trend around vehicles like the Tesla Model 3 mimicking that approach in all-wheel drive applications where we have an induction motor on the front and a permanent magnet synchronous motor on the rear doing the majority of the work. So I suppose this means ultimately that 95% of the motors on the market being used on the market will require magnets still. Of course, there is an interest in getting rid of the cost and the sourcing challenges associated with magnets, but we still expect that by 2030, around 95%, 94% will still require magnets. So think about the e-axle trend specifically, this being the dominant form of motor really for everything up to 6 tons gross vehicle weight. We think that this induction motor market will be bigger, around 13% of the market by 2030 and in 2023, and by 2030 it'll be 10% of a much bigger market. So it continues to show the importance of magnet-based technology. In terms of, let's say, a further level of segmentation, when it comes to the e-axle, there is a sort of separate subdivision of e-axle called e-beam, which we've increasingly been researching. It's a relatively small portion of the light passenger vehicle market, only about 1% by 2030. But this is really important for the pickup market, especially in the US and more, especially the heavy duty end of the pickup market, where we see that the e-axle will be integrated into an existing kind of leaf spring beam axle layout. We think that this will be important for let's say mass adoption of electric pickups. When we go deeper, we recently launched a new forecast around rotor stator technology, and we particularly want to do this to shed light on that aspect of the supply chain, who's supplying the rotor, who's supplying the stator, and the geographic and technical diversity of that. And probably one of the key findings on this is around the winding types in the motor. So in particular on the stator, the growth and importance of let's say U-bend hairpin winding growing from around 44% of the market in 2023 up to 67% of the market by 2030. And this is largely at the expense of insertion or round wire motor technology. So kind of a change in market. I would say more, we're not moving away from magnets anytime yet. They will remain a really integral part of motor design. And this is something that the team are focused on understanding, as I say, the geographic diversity of this, who's working with whom on what particular technology, and how this varies market to market and application to application.
All right, very good. Interesting. Thank you, Graham. Shifting back to Jason then, in terms of the type of work DSD conducts, can you give some context on the type of electric motor development work you are engaged in and whether these industry trends resonate?
Yeah, I mean, well, first to answer the latter part of that question, they 100% resonate. I think this is what we see coming in, the inquiries from our customers, just the discussions we have, what we see at conferences and, across the board. So I think the trends are very much present on the ground, if you will, as well. So the first part of your question, so DSD, I mean, what we do or what we can do is essentially clean sheet design all the way till A sample or B sample prototype test and development. Now, we can do that whole span of work, but we don't always do that whole span of work. And sometimes we do bits and pieces of that depending on where our customer is in the development process. And actually, a lot of what we do and a lot of what we see, and it goes back to what Paul said about getting exposure to our customers' thinking of the future and their product strategy even, is concepting. So our customers come to us and, it does depend on the customer. Typically OEMs, they have a large team with a lot of experience that are focused on the most pressing product development tasks or engineering tasks in the business. So they'll come to us, usually their advanced teams or their advanced teams that are looking, okay, what's next, right? They have a general idea of where they want to go, but they really want to look at the emerging technologies, both frankly motors, but also inverters, and figure out what makes sense for the next, 5-10 years down the road. And so, we take a very system-led approach at DSD, and we look at, we help these customers, and in this particular instance, sort of assess the various motor technologies and topologies, analyze it at a system level, and help them develop, a product strategy for the future. So we see that quite a bit. And then, if we're lucky, we sort of get to stay with them into that A sample phase of the next product, right? So we've done a concept phase. We've worked with them, collaborated with them to sort of narrow the trade space down. And we say, yeah, look, this is the type of thing that's going to meet your requirements. And then we would love, and we do tend to do this as well, take that concept and go into the detailed design, do the prototype procurement, build it, test it, and help our customers get off the ground for that next generation product. I think the shift that we've been kind of talking about, we've definitely seen the induction machine interest from our customers. It's not always what comes out of our concept studies as the direction to proceed, but it definitely is at the forefront of those inquiries, saying, hey, we do want to look at what is out there, what potential we have to get rid of, rare earth magnetic materials. So it's definitely trendy. And I think, there's supply chain things that are driving that. There's costs that are driving that. So it makes sense. So I talked kind of a bit about an example that we would typically get in with, say more of an OEM or a tier one that has a large internal team that has similar expertise to us, but wouldn't have as much of a broad exposure. Those types of projects are often sort of automotive centric or most often come from our automotive customers. If you look at the other industries we're in, it's generally, automotive leads typically with these types of things. So in commercial vehicle, in aerospace and off highway, we often actually come in as the people those customers don't have the expertise, right? So they're not just looking for somebody that has a broad perspective that can concept out and do a system analysis and help choose the path forward. They're actually looking for expertise to bring in-house or not bring in-house, but to leverage to get their products, on the market. And so there we play a role that's, we of course want to look at the system level and the concept level and help define what needs to happen. But usually they already have done that. They know what they need. They just don't know how to engineer and manufacture it. And so we come in a little bit later in the process, but still generally clean sheet and offer our expertise and our knowledge in terms of, electromagnetic and mechanical design and manufacturability and assemblability. All the things that we've been doing for a long time that allow us to sort of accelerate our customers' engineering efforts. So, I think to kind of sum things up, the trends that Graham mentioned are very, very relevant, and we get involved earlier in the stages with our customers to help them sort of get off the ground or make decisions. And what we can deliver at the end of the day is developed, validated A sample, B sample pieces of hardware that they can then take into production.
All right. Great. Thank you, Jason. So maybe building on that, Paul, can you shed some light on how DSD approaches clean sheet design for such new projects, and how, if at all, has the development process changed versus traditional mechanical design projects?
Of course. So the big difference to sort of traditional mechanical design projects is it is a multi-physics problem. So we have electromagnetic domain, thermal domain, and mechanical domain all often competing against each other in order to arrive at a suitable solution. So you cannot just focus in one area. It has to work across all of them. So co-simulation, simulating in all of those domains almost concurrently, is essential to have any level of confidence in the design. There are still assumptions built into those simulations and analysis. And you have to understand those and review them and make sure that they are still applicable for the job in hand. There is a great aspiration in the automotive world to validate designs virtually. So everything is done in the simulation world, and you build one prototype. I think we're still quite a long way away from that with these types of products. So actually turning things into hardware, testing them, understanding them, particularly system interactions, which are probably among the most challenging to analyze or simulate, where you're looking at quite a complex system and how it works with other elements within the vehicle. So prototyping is still going to be a key activity, I think, for a while yet. But these high volume manufacturing processes that are often used in automotive, so things like the hairpin winding, to prototype that is still quite a lengthy process. If you're looking at any sort of reasonable number of prototypes, you have to lay down a tool to be able to make that typically, and that is sort of a 3 or 4 month process to design and manufacture that tool. So there is huge emphasis on minimizing development time in order to get to market quicker and to better understand how systems are performing. But there are these notionally fixed lengths of time where shortening them is extremely challenging. So there are new technologies that are coming in to help. So 3D printing is one of the areas, particularly in windings for initial prototypes. And as the technology matures, then the expectation is you'd be able to essentially do more with that technology further down the development process. So you don't have to spend that time and quite considerable money to lay down a tool. But the overall system performance is still very challenging to simulate. Tools are getting better, but we're still not aware of a single environment that would allow you to develop one of these products, an electric drive unit, for example, in a single environment. So we tend to use sort of best of breed tools in specific areas for gear design, casing design, electromagnetics, thermal, and one of our key capabilities is bringing those pieces of work, mostly disparate pieces of work, bringing them together to arrive at a coherent and functional design. Something like noise is a particularly challenging aspect. So you've got electromagnetic and mechanical sources. There's structural transmission of noise and radiation into actual audible noise for the user. That is a very challenging simulation to set up, to generate, to run, and to solve and extract reasonable results from. So part of our capability is having all of those aspects under one roof, and not necessarily a single specialist, but having specialists in those different disciplines that work together very closely means that we can shorten the design cycle as much as possible to support our customers. But yeah, it remains a challenge.
Yeah, and I can add a little bit as well. So Paul just spoke about sort of our simulation tools, which I think most of the listeners will understand and fairly familiar with. Shifting left and doing most of these things, or trying to do as much as you can in the virtual environment. And everything Paul said is 100%. I agree with 100%, and based in experience and some battle scars, I would say, about getting into hardware and seeing what actually happens. One of the things we have done is try to accelerate that, or not accelerate, but shorten that time in with hardware in the test cell. So speaking of battle scars, many of us have, call them horror stories of trying to put an electric machine together with an inverter in a test cell, and, a test plan or a DVP that's supposed to take, let's say 3 months or something, takes 8 or 9, or hopefully not longer, because of these sort of unforeseen issues. So we've invested in some kit, some Hill systems essentially that are specialized for motor emulation, and it takes the output from many of the tools that Paul just mentioned, and it allows you to emulate these motors and power electronics in real time. And you can then go ahead and put your controls in the loop with that model, and you can try to knock down these issues that you would typically in the past find in the test cell that could cause you a lot of troubleshooting, a lot of heartache and headache to get through. And so that is part of our process if we are going into hardware. Is okay, we release the design of the motor, we know the power electronics we're going to use to control the motor. At least we either have a design or we actually already have the hardware. And then while we're waiting for the motor to be procured, because that takes time, again, depending on the technology, depending on the design, of course, we go into this virtual environment and we have the model of that motor, we have the model of that inverter, or maybe we even have the physical inverter, and we have then also the controls that are going to control those things. And we basically go through it's pared down to what is capable and what we find value in the virtual environment. But we go through a DVP of sorts in that virtual environment and make sure, with the fidelity of the models and everything that we have at that given point, we knock down everything we possibly can before the hardware shows up. And we've seen that, tremendous benefit in that once we get to hardware, because, we've solved a lot of issues that we would have had to solve on an expensive test cell, essentially. And the last thing I'll add is, when you set that environment up, you can do a number of things before the hardware shows up. But then also when the hardware does show up and you do inevitably run into an issue with the hardware, you can actually then go back and you can recreate, you can run an equivalent simulation and speed up and narrow down your root cause analysis to figure out what's going on. So incredibly useful for speeding up the overall development cycle. We've been using it to good effect now for a while, and we kind of weave it into all of the projects that we do so we can deliver, higher value projects to our customers quicker.
All right. Yeah, thank you for sharing. Very, very interesting. So lots of interesting developments, not just in the technology itself, but also in how these technologies are being developed. And then looking forward a little bit, of course, there's lots of interest in what future technologies will come to the market and how these will move the game on. Graham, to you first, in terms of what the research shows us, what do you know of looking forward e-motor technology trends?
Yeah, thanks for bringing me back in, Anna. Actually, say a lot of the challenges that the guys speak to really resonate with me, especially as a former noise and vibration engineer. But good to know that a lot of these solutions are being developed and more work's being done up front to tackle some of these problems. Looking forward, I mean, I'd say one of the great things about our research role in S&P Global Mobility is we get to speak to such a wide variety of companies and types of companies and businesses. And, when we think about the e-motor space, speak to people about, what data they need, how they're looking to progress things. Certainly a few key trends do emerge. So this focus around integration, this idea that, now that we're onto fully battery electric vehicle platforms, now that there's this opportunity to make the powertrain a lot more compact, we see that there's a trend towards increasing integration. What do we mean by integration? We talk about the transmission, the motor, the inverter, and perhaps an increasing number of the power electronics components are all getting put into this one quite compact unit. So we see higher levels of power density on the motor itself, and obviously greater desire for efficiency in this combined unit as a result of the more compact design, perhaps even sharing some of the cooling circuits moving forward in order to minimize complexity and really make this a much tighter package. In terms of some of the broader technologies that perhaps would move the needle, we've mentioned about the e-axle and the kind of the kind of convergence on the e-axle technology as the design of choice. And really that e-axle sits quite centrally in the vehicle. A lot of interest has been around in-wheel motors, so the idea that the motor technology sits on within the wheels of the vehicle rather than inboard effectively. Lots of potential advantages of this from a package space, but I would certainly say in terms of what we would say is unsprung weight, something that engineers are always trying to get rid of. We see for light passenger vehicle applications, this is very much undesirable. And for that reason, as well as durability, we have quite a pessimistic view of the in-wheel motor technology and haven't really come across research from our clients or our contacts that kind of makes us think anything other than that. So when it comes to axial flux technology, certainly lots of interest in this in terms of more power dense, more compact technology, which with advances in manufacturing, it's possible to deliver this type of technology. And we see that this is something certainly for the performance sector. A company like Mercedes-Benz acquiring and integrating a company like YASA into their business to serve some of the AMG applications. We don't necessarily see much evidence that this will filter down to more mainstream applications. But as we mentioned before, magnet-free motors, more cost-effective electric vehicle solutions. We think at the lower end of the market, there is a huge drive to try and make, let's say, A segment, B segment electric vehicles palatable for the mainstream OEMs in Western markets. This is something that certainly the macroeconomic landscape is perhaps holding back at the moment. China really taking a lead in terms of being able to deliver these vehicles at the lower end of the market. So we're looking for cost savings everywhere to really find a way to deliver these smaller segment vehicles for mainstream consumers in Western markets.
What do you think, Jason? Anything different to what Graham has identified? I know he's keen to have someone prove him and the team wrong about in-wheel motors. Maybe you can speak to a broader array of applications.
Yeah, so I mean, first of all, I do think Paul is better positioned to answer this one, but I can comment. So the in-wheel motors, I'll say to Graham, it's all about the system, right? So potentially they offer a solution, but it would have to make sense in the system. And I can confidently say we don't see a lot of inquiries or applications where they work. So I think he's probably right, but I wouldn't discount it entirely. I'm sure in some applications when you look at the system, they could be appealing, but maybe they're less. The number of those applications is potentially not so great. But so I think I generally agree with him. Just briefly before I pass it to Paul, because he will be able to speak to this better than I. Obviously we already talked about some of the main technical trends, getting rid of the rare earth materials, going to induction machines. That's a big one. There's also increased interest, I think, in multi-phase machines. So machines that are greater than 3 phases, 5, 6, 9, even greater than that, offers pretty enticing opportunities for power density and torque density, at the expense of more complicated controls and also more complicated and costly power electronics. But there's a system equation there that is worth exploring. And then the other thing I would say from a trend point of view that we see is some interest in more advanced control methodologies that would be focused on performance. People say software is free, right? It's not, but in a sense it is. So there are advanced control technologies out there, say sensorless control being an example, that if you can employ, you can take the same machine, essentially the same machine, and get a little bit better performance out of it by controlling it differently. So that's, I think, some of the trends that I've seen and I'm aware of, but certainly, I think Paul can speak to some of these in more detail.
Yeah. Paul, over to you then. What technological developments really pique your interest, or what are you looking forward to working on?
Of course. There's as Jason and Graham have mentioned, the push for reduced rare earth composition into motors has been and continues to be quite a hot topic for our customers. And there's a variety of different ways that they're looking to address it. So taking a reduction in magnet performance, so the kind of the output of the magnet is affected by the rare earth content. So if you can accept a slightly lower performance magnet, you can eliminate or certainly reduce some of the rare earth elements, or completely eliminate them. So wound-field rotors, externally excited machines, whatever your term for them, is magnet replacement. That is probably the closest runner that we see in the market at the moment in terms of able to at least approach the power and torque density of a permanent magnet machine, and particularly efficiency if you compare it to an induction machine. But other customers are looking at things like high speeding. So if you can spin the motor faster with a higher gear ratio to the wheels, you can make it smaller and save on material. So it's not necessarily eliminating, but it is reducing the rare earth content. That works up to a point, but again, the system view that Jason was talking about is once you get above a certain ratio to the wheels, you generally have to include an extra stage, so another gear pair, bearings, etc. So additional losses within friction and windage within the gearbox. So elements that you might save on the motor, you lose when you implement a gearbox. So again, having that sort of system high level view is absolutely crucial to these kinds of decisions. And quite a lot of work going into materials, so composite materials to help with high speeding. Carbon wraps on rotors being quite a key one at the moment, but even alternative magnets. So getting rid of the reliance on the neodymium based magnet and something like a manganese based magnet or iron nitride. There's quite a lot of interesting research going on in those kinds of fields, and when they filter down into applicable hardware that we can implement into motors, I think it's going to be really quite interesting to see how they compare. Other areas, making things smaller. You still have notionally the same amount of loss to manage, so improving the thermal management for smaller packages, better oil cooling, active rotor cooling, those kinds of elements I think are going to be key to supporting and maintaining the capability of these motors at lower size or higher speed, even down to the iron that's used. So lower loss, higher strength, lower density steel used within the motors being quite a very useful capability for companies that can create and manufacture those properties in the material. Yeah, as more material come online and more research happens, then I think there's going to be still plenty of activity in sort of developing these refinements to this technology.
All right, very good. Thank you, guys. And maybe a final question around supply chain constraints. And Graham, I know you and the team encounter or hear of lots of issues that can broadly impact EV manufacturing and therefore availability, straddling many sectors. Can you outline some of these?
Yeah, sure. Be glad to. I mean, obviously, we're talking about motors here today, and I think one of the kind of key areas that often comes up in dialogue with our clients and with some of the people that we interface with on the research side is the availability of electrical steel. So electrical steel is not the same as regular steel, and really in the composition of that motor, the fact that we have these really thin steel laminates. The ability it's a very specific grade of electrical steel that delivers the high performance we want from these motors. So availability of that electrical steel, but also the availability of the manufacturing capability and the machinery to stamp it, to get those high power densities we need very thin electrical steel. There's actually a very limited number of companies that can make that stamping machinery to achieve that. So that really is an area of focus, or perhaps even an opportunity for companies who are in that area. Certainly, availability of rare earths, as has been mentioned, is a potential constraint, and the geopolitical aspects of that I alluded to. The idea that China might somehow try to ring fence their large natural resources of these critical rare earths, some of which Paul mentioned there before. This is encouraging the engineering community to look elsewhere for other options, or of course have to be very careful in how they manage what they have access to. Maybe more broadly, away from specifically motors, of course, lots of question marks around how availability of critical battery raw materials might hold back the electric vehicle adoption curve, particularly lithium and cobalt. And when we work together with our colleagues in the metals and mining division of S&P Global Commodity Insights, we put our demand with their supply together, and we can potentially see shortfalls as soon as 2027 for the lithium, 2026 for the cobalt. But obviously, aside from pure battery kind of availability in terms of the materials and the number of gigafactories, again, some more kind of local constraints around things like drying machinery in the gigafactory. So being able to dry out the cathode material before it's installed into cells, quite an energy intensive process, and very few companies around the world who can make that machinery. And then, of course, we've had several complete podcasts on the topic, but of course, charging infrastructure is a broader, bigger issue, holding back electric vehicle adoption and leading to a degree of skepticism in consumers in major markets, never mind markets where we might expect access to reliable electricity, where we might dwell will be even more challenging. So there's definitely a bigger topic around charging infrastructure. We'd quite like to put the topic back to Jason and Paul, really, and see, do these comments resonate, particularly the electric motor and the e-steel aspects. Maybe any more comments more broadly on what might derail electric vehicle uptake?
Yeah, absolutely. So, as you've said, the availability of electrical steel, and as we've discussed earlier, actually getting hold of a small quantity of steel to support prototype builds it can be extremely challenging, and it's one of those things that is very difficult to change later in the development process. You can't substitute it and expect to put in an alternative later. So yeah, it definitely can hamper the development process and the implementation of it due to the availability of these kinds of materials. And simply something like cost of complexity or a make-buy decision at the vehicle manufacturer, particularly the larger companies where they may have a range of products across different platforms and more than likely different brands. You've got different customer perceptions of the driving experience of those vehicles, and that may drive different performance criteria. So is it best to have one motor that fits all, and some vehicles are carrying extra mass, cost, weight in than they strictly need to, but the larger, higher performance vehicles more meet the criteria, or do you have a variety of different powertrain systems that meet every application directly. And do you buy some of those elements and make the others, or how do you make that decision? How do you look at that? So an overall sort of strategy view of how parts are or how systems are designed for traction applications is a fiendishly complicated challenge for a lot of companies, I think.
Great. Thank you. Unfortunately, that's all the time we have for today. A big thank you to our guests, Jason and Paul, as well as Graham, for joining Autology and sharing your insights.
Thank you, Anna. Thanks very much for having us. Thank you, guys.
Thank you.
Thank you.
Thanks.
All right. And thank you to all you listeners for tuning in as well. We'd love to hear your thoughts on today's episode at our autology@spglobal.com email. And you can find out much more at autotechinsight.ihsmarket.com. Don't forget to hit all the subscribe, follow, and like buttons to stay on track with the latest Autology podcast. And we look forward to you joining us again in the next episode. Bye for now.